Good morning. So today we shall study the superposition theorem. In earlier videos we have studied the Thevenin theorem and Norton's theorem. In accordance with the Thevenin's theorem, any two-terminal linear network can be simplified in terms of a constant voltage source in series with an equivalent resistance or Thevenin resistance. And in accordance with the Norton's theorem, any complicated network can be simplified with a parallel circuit consisting of a constant current source in a parallel with an equivalent resistance called Norton resistance. In both these theorems, we have seen that there was only one source of EMF used. But if the given network contains two or more sources of EMFs, we need to apply the superposition theorem, or the analysis also can be done by using the Kirchhoff's laws. But we have seen that application of the Kirchhoff's laws for analyzing the given complicated network is a very lengthy process, it is a very tedious process, and hence it is a time consuming process. So if we are interested to analyze the given network with ease in a short interval of time, we can do it by using the superposition theorem. So let us see first what is this superposition theorem. The statement of the superposition theorem is like in a linear bilateral network, if there are number of voltage or current sources acting simultaneously, then the current passing through a certain component or the potential drop across a certain component is equal to the algebraic sum of the currents or voltages produced independently by each source. So that is the statement of the superposition theorem. You can listen to it carefully once again. In a linear bilateral network, if there are number of voltage or current sources acting simultaneously, then the current through or the voltage across any element is equal to the algebraic sum of the currents or voltages produced independently by each source. So that is the statement of the superposition theorem. Now, when we want to obtain the effect of each individual source, what we need to do is we have to temporarily kill the other source. And find out the current or the voltage across the required element of the circuit due to each individual source, and then take the algebraic sum of the currents or the voltages across that element due to all the sources. So whenever we want to kill a certain source, if it is a voltage source, then that voltage source should be killed for its EMF, retaining its internal resistance in the circuit. And if there is a current source, then the terminals between which the current source is connected should be open circuited. The reason is that when we consider the voltage source, the internal resistance of the voltage source is very low, so as good as if it is short circuited. And since the internal resistance of the current source is very high, it is as good as if it is open circuited. So when we want to temporarily kill the source, if it is the voltage source, it should be short circuited for its EMF, retaining its internal resistance in the circuit. And if it is the current source, then it should be open circuited. And then find out the effect due to each individual source and take the algebraic sum of the currents or voltages across a certain element, across the required element, so that we get the effect due to all the sources. So to understand the use of this superposition theorem, let us consider, for the sake of simplicity, we have a network containing two sources of EMFs and three resistors. Suppose this is the first source of EMF E1, the second source of EMF E2, and the three resistors are R1, R2, and R3. Let us consider R1, R2, R3 are the three resistors, and the two sources of EMFs are E1 and E2. This is the positive terminal, negative terminal, positive terminal, and negative terminal. So this source E1 will send the current I1 through the resistor R1. The source E2 will send the current I2 into the circuit through the resistance R2, and both these currents will approach to the junction, and all that current, that is I1 plus I2, will flow through the resistance R3. At the junction, again the currents will get divided. The part I1 will flow through this branch, and the part I2 will flow through this branch. Suppose we have this network A, B, C, D, E, F, and E. So let's consider we have this network. So we want to analyze this network by using the superposition theorem. Before we apply the superposition theorem for the analysis of this given network, let us first try to obtain the expression for the current flowing through the resistance R3 by using the Kirchhoff's laws. Let us first obtain the expression for the current I1 plus I2 flowing through this resistance R3 by using the Kirchhoff's laws, and then we shall apply the superposition theorem for the analysis of this network, and let us compare, we shall calculate the total current flowing through this resistance R3 by application of the superposition theorem. And if we observe that the expression for the total current I1 plus I2 flowing through the resistance R3 by application of the Kirchhoff's laws and by applying the superposition theorem if both these expressions are same, then we can say that the superposition theorem is verified. So let us first analyze this network by using the Kirchhoff's law. So we have said that when we want to apply the Kirchhoff's law, we have to write down the voltage equations for the different loops in the given network, and by solving these voltage equations simultaneously, we can find out the required current. So let us first apply this Kirchhoff's voltage law to the loop A, B, E, F, A. Suppose we want to apply this Kirchhoff's voltage law to this force loop. So if we apply the Kirchhoff's voltage law to this force loop, what we can write is, we can write I1 R1 plus I1 plus I2 into R3 is equal to E1. Or this can be simplified and expressed as I1 into bracket R1 plus R3 plus I2 R3 is equal to E1. Say this is equation number 1. And if we apply the Kirchhoff's voltage law to the second loop C, B, E, B, C, for the second loop, the voltage equation for this second loop can be expressed as I2 R2 plus I1 plus I2 R3 is equal to E2. Or by simplifying, we can express this relation as I1 R3 plus R2 plus R3 into I2 is equal to E2. So this is equation 1, 2. So by solving these two equations 1 and 2, we can obtain the expressions for the values of I1 and I2 in terms of E1, E2, R1, R2 and R3. So for that purpose, what we need to do is, we have to eliminate either I1 or I2 from equations 1 and 2. So let us first eliminate I2 from this expression, so that we will get the expression for I2. To eliminate I2 from these two equations, what we need to do is, we have to multiply equation 1 by R2 plus R3 minus equation 2 multiplied by equation 2 multiplied by R3. So taking the subtraction, multiply equation 1 by R2 plus R3 and equation 2 by R3 and take the subtraction, we shall get I1 into bracket R1 plus R3 into R2 plus R3 plus I2 R3 into bracket R2 plus R3 is equal to E1 into bracket R2 plus R3. This is equation we get by multiplying equation 1 by R2 plus R3. Similarly, multiply equation 2 by R3. Multiplying equation 2 by R3, what we shall get is I1 R3 square plus R2 plus R3 into R3 I2 is equal to E2 R3. and taking the subtraction of these two expressions, this term, taking subtraction means we have to change the signs of all these terms. So this is plus I2 R3 R2 plus R3. This is minus I2 R3 R2 plus R3. So these will get cancelled, and from these two terms if we take I1 R1, we can write I1 into bracket R1 plus R3 into R2 plus R3. If we take the product of these two brackets, we will get R1 R2 plus R1 R3 plus R2 R3 plus R3 square is the product of these two brackets minus R3 square is equal to E1 into R2 plus R3 minus E2 R3. So this plus R3 square minus R3 square will cancel. So we get the expression for I1 to be equal to E1 into bracket R2 plus R3 minus E2 R3 divided by R1 R2 plus R2 R3 plus R3 R3. So that is the expression for I1. And similarly, we can obtain the expression for I2. To obtain the expression for I2, we have to eliminate I1 from equation 1 and 2. To obtain the expression for I2, we have to eliminate I1 from equation 1 and 2. So, let us write this expression for I1 here. I1 is E1 into bracket R2 plus R3 minus E2 R3 divided by R1 R2 plus R2 R3 plus R3 R3. So let us eliminate I1. To eliminate I1 from equations 1 and 2, what we need to do is we have to multiply equation 1 by R3 and equation 2 by R1 plus R3 and take the subtraction. So equation 1 multiplied by R3 minus equation 2 multiplied by R1 plus R and take the subtraction. So equation 1 multiplied by R3 is I1 R3 into bracket R1 plus R3 plus I2 R3 square is equal to E1 R, and multiply equation 2 by R1 plus R3 we get I1 R3 into bracket R1 plus R3 plus R2 R3 plus into R1 plus R3 into I is equal to E2 into bracket R1 plus R3. And taking the subtraction, we get this term will get cancelled. So it is I2 into bracket I2 into bracket. This is if we take I2 common from these two terms into bracket, it is R3 square minus every term will be negative. And the product here will be R1 R2 plus R1 R3, it should be minus minus R1 R2 E1 R1 minus E2 in the bracket R1 plus R2. So this plus R3 square minus R3 square cancels. So we get the expression for I2. Here every term is negative, so we can take the negative sign common. So we can change the sign on the right hand side also. So I2 will be equal to E2 into bracket R1 plus R2 minus E1 R2 divided by R1 R2 plus R2 R2 plus R3 R2. So this is the correct I2 set by the source E2 in this loop. So knowing the expression for I1 and I2, now we can find out the total current flowing in resistance R3, and it is equal to the sum of these two currents. So I1 plus I2 will be equal. Therefore, total current R1 is I1 plus I2. So I1 is E1 into bracket R2 plus R3 minus E2 R3 divided by R1 R2 plus R2 R3 plus R3 R1 plus I2 is E2 into bracket R2 plus R3 minus E1 R2 divided by R1 R2 plus R3 R3 plus R3 R. I am taking this LCM, we can express it as R1 R2 plus R2 R3 plus R3 R1, and numerator will be taking separating this bracket, we can express it as E1 R2 plus E1 R3 minus E2 R2 plus E2 R1 plus E2 R3 minus E1 R2. So which terms will cancel? This is minus E2 R3 and here it is plus E2 R3. So these two terms will cancel. There it is minus E1 R3 and here it is plus E1 R3. These two terms will cancel. So the net total terms are E1 R2 plus E2 R2 divided by this. So the total current passing through the resistance R3 is I1 plus I2 is equal to E1 R2 plus E2 R1 divided by R1 R2 plus R2 R3 plus R3 R. This is in accordance with the Kirchhoff. This is the total current flowing through this resistance R3 in accordance with the Kirchhoff. Now we want to apply the superposition theorem to find out the current flowing through this resistance R, current through R3 by using Kirchhoff's law. Using superposition theorem, current through R3 using superposition theorem. Now, when we want to apply the superposition theorem in order to determine the current flowing through this resistance R3, We have to obtain the current flowing through this resistance R3 due to the individual sources of EMFs, and for that purpose we have to kill the other sources of EMFs temporarily and find out the current through the required element. So here let us first obtain the effect of E1 or the current flowing through this resistance R3 due to E1, and for that purpose we have to kill E2 for its EMF, retaining its internal resistance in the circuit. In the given network, no internal resistance is mentioned, so it must be G. So if we kill the E2 for its EMF, the network we get will be of this type. This is E1, this is R1, R3, R2, and E2 is killed for its EMF temporarily. So this is E1, R1, R2, and R3. Let I1 prime is the current flowing through R3. I1 prime is the current flowing through R3 due to E1 only. And the current flowing through R2 due to E1 is I2 prime. Such that the current flowing through R1 will be I1 prime plus I2 prime. The current sent by E1 in the circuit will be I1 prime plus I2 prime, such that the part I1 prime flow through R3 and the part I2 prime flow through R1. And the current flowing through R1 is I1 prime plus I2 prime. Now, in order to find out the expression for I1 prime in terms of E1, R2, R1, R2 and R3, what we need to do is we must first know the total resistance of this circuit. Here, if we observe this network, the total resistance of the circuit is nothing but R1 plus R2 parallel R. And let Rx is the equivalent resistance of transformation of R2 and R3. Then it is expressed as R1 R2 upon R1 plus R. So the total resistance of the circuit works out to be equal to is R1 plus R1 R2. It is not parallel operation of R1 R2. It is parallel operation of R2 and R3. So it is R1 R3 divided by R2 plus R. So that is R2 R3 upon R2 plus R3. So it should be R2 R3 divided by R2 plus R. So if this is the total resistance of this network, then the current I1 prime plus I2 prime sent by the source E1 will be equal to the EMF of the source E1 divided by the total resistance of the circuit. It is R1 plus R2 R3 upon R2 plus R. So taking LCM here, R2 plus R3, this can be expressed as this R2 plus R3 will go to the numerator. So it is E1 into bracket R2 plus R3 divided by R1 R2 plus R2 R3 plus R3 R. This is the total current I1 plus I1 prime plus I2 prime sent by the source E1 in the circuit. Now, out of this total current I1 prime plus I2 prime sent by the source E1 in the circuit, the part I1 prime flow through R3 and the part I2 prime flow through R2. So, how to obtain this current I1 prime and I2 prime. So here, since here we observe that the resistors R2 and R3 are connected in parallel. Since here we observe that R2 and R3 are in parallel combination. So what we can say is that we can say that the potential drop across R2 and the potential drop across R3 must be equal. And these individual potential drops across R2 and R3 again must be equal to the potential drop across the parallel combination of these two resistors. So, equating the potential drops across R2 and R3, we get when the current I2 prime flow through R2, the potential drop across R2 will be R2 into I2, right? And this must be equal to when the current I1 prime flow through R3, the potential drop across R3 will be R3 into I1 prime, and this must be equal to the potential drop across this parallel combination. The current flowing through the parallel combination is I1 prime plus I2 prime, and the equivalent resistance of the parallel combination is Rx. So this Rx is nothing but equal to R2 R3 upon R2 plus R1. So this is equal to I1 prime plus I2 prime into R2 R3 upon R2 plus R2. And we have obtained the expression for I1 prime plus I2 prime. The expression for I1 prime plus I2 prime is this. So using this expression here, we can write this as, we can express this expression as R3 into I1 prime is equal to R2 into I2 prime is equal to I1 prime plus I2 prime is replaced by this expression. So it is E1 into bracket R2 plus R3 divided by R1 R2 plus R2 R3 plus R3 R1 into R2 R3 divided by R2 plus R3. So here this R2 plus R3, R2 plus R3 will get cancelled. So we get the expression like this. We get the expression like this. This R3 I1 prime equal to R2 I2 prime is equal to E1 R2 R3 divided by R1 R2 plus R2 R3 plus R3 R3. And now we can obtain the expression for I1 prime and I2 prime separately. So here, if we equate the first term on the left side and the last term on this in this expression, we get R3 I1 prime is equal to E1 R2 R3 divided by R1 R2 plus R2 R3 plus R3 R2. So this R3 will get cancelled. So this implies I1 prime is equal to E1 R2 divided by R1 R2 plus R2 R3 plus R3 R2. So this is the current I1 prime that flows through R3 only due to E1. And similarly, by equating these two terms, we can obtain the expression for I2 prime. So R2 I2 prime is equal to E1 R2 R3 divided by R1 R2 plus R2 R3 plus R3 R1. So this R2 R2 will get cancelled. This implies I2 prime is equal to E1 R3 divided by R1 R2 plus R2 R3 plus R3 R3. So this is the current I2 prime that will flow through R2 only due to the source E1. So this is the expression for I1 prime and I2 prime. So we have found out the current flowing through R1, R2 and R3 only due to the source E1. And for that purpose, we have temporarily killed the source of EMF E2 for its EMF by retaining its internal resistance in the circuit. So remember these two expressions for I1 prime and I2 prime. I1 prime is E1 R2 upon R1 R2 plus R2 R3 plus R3 R1, and I2 prime is equal to E1 R3 divided by R1 R2 plus R2 R3 plus R3 R1. These are the expressions for I1 and I2. It is the effect due to the source E1. Now, let us obtain the current with this resistance R3 due to the source E2. Due to the source E2, and for that purpose, we have to kill the first source E1 for its EMF by retaining its internal resistance in the circuit. So, if we kill the first source of EMF for its EMF, retaining its internal resistance in the circuit, the net work we get will be of this type. This is the source E2. This is the resistance R1. This is R2 and this is R. So let us consider the total current sent by the source E2 in the circuit is I1 double prime plus I2 double prime. The total current sent by the source E2 in the circuit is I1 double prime plus I2 double prime. So that this total current will flow through this resistance R2. At this junction, the part I1 double prime flow through R2, R3, and the part I2 double prime flow through R2. So here we can obtain the expressions for I1 prime, I1 double prime, I2 double prime, and I1 double prime plus I2 double prime. So for that purpose, we must first know the total resistance of the circuit. Total resistance of the circuit is equal to R2 plus R1 R1 R. Here we observe that the total resistance in the circuit is the series combination of R2 and parallel combination of R1 plus R3 connected in series with R1. So this is the total resistance of the circuit. So this is equal to R2 plus R1 R3 upon R1 plus R. Therefore, the total current sent by the source E2, that is I1 double prime plus I2 double prime, works out to be equal to E2 divided by the total resistance of the circuit is R2 plus R1 R3 upon R1 plus R. For this can be expressed as E2 into bracket R1 plus R2 divided by, if we open up, take the multiplication with this term and open the bracket, we can express that this is nothing but R1 R2 plus R2 R3 plus R3 R1. So this is the total current saved by only E2 in the circuit in the absence of E1. So here it is observed that the resistors R1 and R3 are connected in parallel such that the potential drops across R1 and across R3 must be equal, and again these potential drops are equal to the potential drop across the parallel combination of R1 and R3. So equating the potential drops across R1, R3 and across the parallel combination, we can express this as R1 I1 double prime is equal to R3 I2 double prime is equal to I1 double prime plus I2 double prime into Rx. And Rx is equal to R1 R3 upon R1 plus R2. So if we use this expression for I1 double prime plus I2 double prime here, we can write this expression for potential drops across R1, R3 and the parallel combination as R1 I1 double prime is equal to R3 I2 double prime is equal to the expression for I1 double prime plus I2 double prime is the expression for I1 double prime plus I2 double prime is this E2 or this E2 upon R2 plus it is simplified E2 into bracket. It is R1 plus R2 divided by R1 R2 plus R2 R2 plus R3 R1 into R1 R3 upon R1 plus R2. So this is the expression by equating the potential drops across R1, R3 and across the parallel combination. We get this expression. So here we can obtain the expressions for I1 double prime, I2 double prime by comparing the first term and the third term, and by equating the second term and the third term. We can write equating the first term and second term, we get R1 I1 double prime is equal to this here. This R1 plus R3 will cancel. So it is E2 into R1 R3 divided by R1 R3 plus R2 R3 plus R3 R3. So this R1 will cancel. So this implies the expression for the current I1 double prime that flows through R3 only into E2 in the absence of E1. And I1 double prime is equal to E2 R3 divided by R1 R2 plus R2 R3 plus R3 R. This is the current I1 double prime that flows through R3 only due to E in the absence of E1. And equating the second and third terms, we can express it as R3 I2 double prime is equal to E2 R1 R3 divided by R1 R2 plus R2 R3 plus R3 R1. So this R3 will get cancelled. So this implies I2 double prime is equal to E2 R1 divided by R1 plus R2 R3 plus R2 R3. So these are the expressions for I1 double prime and I2 double prime. These currents only due to the source E. So in the presence of both the sources, what will be the current flowing through this resistance R3? That is what we are interested to know. Only due to E1, we have said that the current flowing through R3 is I1, and only due to E2, the current flowing through R3 is I1 double. So that the total current flowing through the resistance R3 in the presence of both these sources of EMFs will be therefore current through R3 due to both E1 and E2 is I1 prime plus I1 double prime. I1 prime is the current through R3 only due to E1, and I1 double prime is the current through R3 only due to E2. So using these expressions for I1 prime and I1 double prime here, we get E1 R2 upon R1 R2 plus R2 R3 plus R3 R1 plus I1 double prime is E2 R3 divided by R1 R2 plus R2 R3 plus R3 R1. So this is the total current that will flow through the resistance R3 in the presence of both the sources of EMFs, E1 and E2. So this is it. If we take this LCM, we have R1 R2 plus R2 R3 plus R3 R1, and in the numerator it is E1 R2 plus E2 R3. E1 R2 plus E2 R3. This is the total current I1 prime plus I1 double prime that will flow through the resistance R3 in the presence of both the sources of EMFs obtained by applying the superposition theorem. This current is obtained by applying the superposition theorem. So, if we compare this expression for I1 prime plus I1 double prime with the current I1 plus I2 that we have obtained for the current flowing through this resistance R3 by application of the Kirchhoff's laws, it is observed that these two expressions are one and the same. So, since I1 plus I2, the expression for the current flowing through the resistance R3 obtained by using the Kirchhoff's laws is same as the expression for the current I1 prime plus I1 double prime flowing through the resistance R3 by application of superposition theorem. So what we can say is that the superposition theorem is verified. So this is equal to E1 R2 plus E2 R3 divided by R1 R2 plus R2 R3 plus R3. So this is how we can say that the superposition theorem is verified. This is how we can say that the superposition theorem is verified, because the expressions for the current flowing through this resistance R3 by applying the Kirchhoff's laws to the circuit and by the application of the superposition theorem to the same circuit, we get the same expression for the current flowing through this resistance R3. So we can say that the superposition theorem is verified. Okay, thank you.